Welcome, everybody, to this sort of trial class, AP Chemistry and Introduction to the United States Chemistry National Olympiad. Just a side note, make sure to have a periodic table pulled out that you can refer to easily, because we will be doing some practice questions, so you might need to know a little bit of information. By the way, my name's Adam Abashir, and I'll get to my introduction right now. So I was born in 1997. I'm 23 years old. I attended Stanford University in 2015, and I graduated with a bachelor's in chemistry and a master's in bioengineering just this year. My experience with the Chemistry Olympiad, I competed twice, back-to-back years, and I did all right. My school didn't have a team dedicated to the Chemistry Olympiad. It was pretty unknown, so I had to teach myself. And the best way to prepare is to, take a AP chemistry course, because that has about 80% of the basic material that you'll need. And I had to teach myself some more advanced stuff like organic chemistry to compete alongside other people who were taking the test. In my free time, I do a lot of self-defense. Not anymore because of the pandemic. That's why we're having a class like this anyway. And also I try to draw and other stuff. If you have any hobby questions, you can ask me. Any self-defense questions, I can definitely answer. So I realize that there are a lot of you here, so I don't think we'll be able to go through everybody, unfortunately. But how about we do this in the chat? Maybe y'all can just send your grade level and then send yes or no if you like chemistry. And I'll take a look here. There are about 30 people, so I expect 30 responses. Ninth grade, love it, excellent. Make sure to send it to the public chat so everyone, maybe can take a look for themselves. All right. Chem is okay. 7th grade, yes. All right. So I don't think I'll be able to know everybody by the end of class, but I will try. 7th grade. Some of y'all are pretty young, so it's a little surprising. We will get to what the competition is a little bit later, and I'll explain sort of what's required to do well and understand. But if you have a chance, if you haven't answered it yet, you can. The grade level, and if you like chemistry, and we'll move on. So what is the competition? Again, maybe you can, I think the chat option lets you do a little hand raise if people have heard of the competition before signing up for this class. We have some people raising their hand. So only 2 people so far. So maybe like when I was taking it, I was the only one that knew about it, so I'm not surprised. I don't think, I'm going to assume no one's actually taken it before, but that could be like wrong. I'm not sure if they have a grade limit for who can take it or who can't. But the competition is designed into 4 sections. So if you've ever taken a math counts or math competition course, you would understand this would be a little bit familiar, but basically it starts out with a local competition where each region hosts its own test, or they borrow the local exam from the American Chemical Society, which hosts the test. And it's just a 60 question multiple choice test, and if you do 50 or above, or whatever criteria that the region sets to select you, then you will be chosen to move on to the national exam. So the national exam is a lot more standardized across the whole nation, where it's divided up into 3 parts: a 1.5 hour multiple choice test, a 1 hour and 45-minute free response test, and a 1.5 hour laboratory practical. And from all the people in the country that take the test, only 20 are chosen to go to this study camp where they do a really intense and rigorous training course, and they test you at the end of it and see who the best 4 students are to go and take the ICHO, so ICHO, International Chemistry Olympiad. And that involves a 5-hour theoretical exam and a 5-hour laboratory practical. So pretty intense, a little bit shorter than other competitions for like USNCO or IMO, in my opinion. Yeah, Sophie, I know what you're talking about. That it is a lot to spend 5 hours doing a test, but I assume they train you well enough to do that. When I was in college and I took my laboratory classes, we would spend up to 6-7 hours doing chemistry straight. So you, you get used to it when you get older. So something to look forward to if you get past the national exam. So we have a lot of people who love chemistry. Have you ever thought about what defines or what the definition of chemistry is? Because it seems obvious, but it actually is one of the, I think, broadest sciences because of how applicable it is with so many other fields of study. So I have down here the study of substances and their interactions, and that's pretty much as general as I can make it, where we study, what composes the substances, how the substances react with other substances, how the molecules in something are affected by temperature, other physical phenomenon, and you can also think about how chemical structures organize into large biomolecules like proteins and carbohydrates, and all that is still chemistry. So I have a nice little list here that sort of breaks up what AP chemistry is and advanced chemistry. Advanced chemistry, I would say, is college level chemistry that you'd be taking past high school. And so you have the typical atomic structure and properties. You have molecular and ionic compounds and their properties. You have intermolecular forces, how molecules interact with each other. You have chemical reactions, where we actually have molecular bonds or chemical bonds being broken and changed. You have kinetics, the rate at which reactions happen, thermodynamics. You have equilibrium, acids and bases, and free energy and electrochemistry. And the test covers all of this. You have to know about free energy, you have to know about equilibrium, you have to know about all these topics. You also have to know about some, I would say, pretty specific, like chemistry trivia questions almost, like what industry uses, or where does the chemical industry obtain gold from? question like that could be definitely seen on the chemistry test. As for the advanced chemistry, the local and national exams definitely include organic chemistry and some analytical chemistry in terms of techniques and laboratory practices, but you shouldn't be seeing theoretical chemistry, biochemistry, pharmacology, those advanced topics until the study camp or the international exam. Does anybody have any questions so far? You can unmute your mic and say something. I'll wait 5 seconds. All right. If you have any questions, you can also type it in the chat. I'm trying to keep up as well. So, all right. You need to know everything from this list. So let's go backward. Let's see if I can do that. If you want to do really well on the test, you need to know everything in the AP Chemistry topics list for sure. You will need to know some organic chemistry, and you'll need to know some analytical chemistry for the local and national exams. Getting to the national exam in and of itself is a really impressive achievement. Getting farther than that, definitely gonna make you noticeable in colleges. Trying to learn all this stuff in high school, though, on the advanced chemistry topic will be a little bit difficult. So I think I have a couple more questions. We are doing mostly AP chemistry. I think depending on how people feel about the class, we might transition to more advanced topics depending on everyone's experience. I've seen, multiple grade levels. I'm not sure how everyone feels, and I will talk with the people at Momentum to see how y'all feel. Hopefully you give some good feedback on what you'd prefer to learn. For a textbook, I haven't chosen one specifically for y'all to use. I was hoping I could just provide you the information directly. But if you feel like going above and beyond, I'm just pulling from a regular chemistry textbook that covers general principles. To try and teach yourself organic chemistry, I have a couple of recommendations that I could maybe send at the end of the class. All right, so, and as I was saying before, advanced topics, I learned most of it in college. So I had help learning inorganic chemistry and biochemistry. I was able to teach myself a bit of organic chemistry in high school, but that took extra time. So hopefully, after, again, considering feedback, we'll see what exactly we want this course to be. All right, so just to warm up a bit, here is a question taken from the local exam, and I will give y'all a minute or two to think about it, and then give me an answer. You can type it in the chat, you can send it privately, your call. All right, I see some answers coming in. This is it's not an obvious question or not an obvious answer. If you don't think about what barometers are used for, and if you don't know something about mercury and water, I'll give maybe 10 more seconds And while I do that, I'm going to draw a little hint. I'm going to draw what a barometer looks like. So let's say you have, oh, that's not good. Let's say you have a little tube here. You have a tub. You have a liquid here. This is a typical mercury barometer. You have fluid here. This has 0 atmospheres, let's say. All right, so I'm seeing a lot of D. This is a question that you could maybe answer just from a process of elimination. So first of all, we should consider what facts are true and what facts aren't true. I don't think, well, one, we know mercury has a higher boiling point than water. It's a metal. Although it's a liquid as well, the boiling point of mercury is around 600 degrees Fahrenheit. We know it's a true fact, but we should ask ourselves what that has to do with a barometer, which measures air pressure, right? Mercury is chemically unreactive compared with water. That's, a little true. I would argue that mercury is able to interact with a lot of organic compounds, and so to try and say that it's chemically inert is a little misleading. But also, I guess you would be worried about it reacting with air. That's not the case. For D, I see a lot of people said D. Mercury expands with a decrease in air pressure. Water does not. I don't think either of those are true, where mercury expands with a decrease in air pressure. Mercury's, if mercury was to expand with a decrease in air pressure, so would water. So by process of elimination, we might see that A is becoming the relatively correct answer, but it's important to know why that's the case. So I drew the little barometer down here. So we consider the atmosphere pressing down on this device here. We have air pressure pushing in the tub, making the fluid, whatever it is in here, go up. And so whatever relative difference you see between the initial marking, right, and the, let's say, final marking right here, this is your change in air pressure relative to what we know Earth's normal atmospheric pressure is, which is around 760 milligrams of mercury. So mercury, being much denser than water, doesn't require nearly as much space to actually give you an accurate measurement. So if I have mercury, I can save money and save time building this apparatus, where if I had a water barometer to measure changes in air pressure, let me undo that, I would have to have this little tube pretty much extend all the way through the answer choices if I wanted to measure the same change in air pressure compared to mercury, right? And this is unpractical. We don't want to see that. Does that make sense, everybody? All right, I have 2 yeses. That's pretty good. Great. So for this question, I did a lot of the solving. Maybe the next one, I'll call on one of you to try and solve it for the class. How about that? I'm gonna clear the drawing. Any questions, by the way? All right, let's move on. Stop annotating. So What is the mass of one molecule of water in grams? Go ahead. This time I'm going to call on someone to help me out. 10 more seconds. All right. So I'm going to select Jack Fan chose the easy way out without using a calculator. I respect that. Sophia Zhang, actually, Sophia Z, sorry. Sophia Z apostrophe or period. Can you maybe explain exactly how you got to your answer, C, if you wouldn't mind? And if she is willing to unmute. All right. Well, how about she typed it out, yeah. I was hoping for more of a in-depth explanation, but I can go ahead and just explain. So yeah, exactly. We're taking we understand based on the periodic table, we can calculate the mass of water to be equal to 1 times 2 plus 16. These would technically be in atomic mass units or grams per mole, right? Grams per mole. This will give us 18 grams per mole of material, where a mole is equal to 6.023 times 10 to the 23 molecules, right? It's like a dozen, but instead of a dozen, we have a mole of molecules. So if I wanted to find the mass of one molecule, I would just take my grams here, 18 grams per 1 mole, and I'd multiply that by 1 mole over 6.023 times 10 to the 23 molecules. Sorry, running out of room here. And if you do the math, you get about 3.0 times 10 to the negative 23 grams. All right, so someone typed in the chat for us, which is very nice. Great. Does that make sense? 5 quick seconds. 5, 4. You can definitely be honest. 3, 2, 1. All right. So which hydrocarbon is 84.1% carbon by mass? Good job, Jack. Calculators are your best friend. All right. I think everyone so far doing well. So I'll just explain. This is sort of a trial by error question and a can you read the periodic table question, right? So you would just go and you calculate the mass of each one. If I was to do that, this would be like 16 grams per mole. This would be, oh, you have 12 over 16, the carbon to total mass ratio, 24 over 30. This would be 48 over 58. And this would be 96 over 114, which people have typed out. This is 75%, not enough. 80%, not enough. This is like 82%, and this turns out to be 84%. So quick and simple, can you do math sort of question. Yeah, exactly, Jean-Michel. All right, so that was a quick one. How about this next question? Molarity of sodium ions in a solution prepared by diluting 250 milliliters, 0.55 moles sodium sulfate to 1.25 liters. 0.55 molar, sorry. All right. 10 more seconds. If y'all want to, type the solution to me, make sure to do it privately, just so we don't spoil the answer for people who are thinking. All right, so I think everyone is in the ballpark of being correct. I'm sure y'all use this nice handy formula where if we have the molarity of one solution times the volume of one solution and we dilute it, we know that it will equal the molarity afterward times the volume afterward, right? So exactly, Angela typed it out in the chat. We would have 0.55 mole times, we have to make sure our units are consistent across, so it'd be 0.250 liters is equal to this unknown molarity times 1.25 liters, right? So we have to be careful of the molarity that we're calculating. This value here is the molarity of sodium sulfate in its entirety, right? So on the end, this will also be the molarity of sodium sulfate in its entirety, right? That's the concentration in the solution. So after we do the math, we get M2 is equal to 0.11. But as Jack has expressed, you have to consider the sodium ions. So we have to multiply this concentration by 2 because there's 2 sodium ions for every sodium sulfate ion. Molarity, yeah, so molarity is equal to the moles of solute over the volume of solution. I think someone is correct, it's specifically liters. So we always have mole per liter is equal to molarity. There's a different value, molality, which you haven't heard of. That is a different way of measuring concentration. Yes, there you go. All right, so we're going to move on to the last question I have. Oh, can you explain why we have 2 times again? Oh, all right, cleared away. Last question. 30 seconds. This is where the organic chemistry starts to come in. You have to know how to read what these mean. Exactly. Correct, Sophie. All right, maybe 10 more seconds. All right, so I think maybe the best way to do this, if you don't know how to read organic molecules yet, I'll just draw them out. Yes, the bandwagon. So cyclopropane, if you've seen skeletal structure before, every vertex is representative of a carbon atom. And these carbon atoms have the maximum amount of bonds possible indicated. So if I don't draw out any bonds, there should be hydrogen molecules coming off of this. So I'm going to draw out the bonds for everybody. So we have cyclopropane right here with a total of 6 hydrogens. So propane itself looks like this with, again, 3 carbon atoms. The suffix or the prefix pro, it's either pro or, yeah, it's prop actually, is equal to 3, indicating that there's 3 carbons. So I'm going to go and draw the maximum number of hydrogens I can. A carbon's able to take 4 bonds. It's stable configuration. So propane has 8 hydrogens. Propene, this suffix indicates that there's a double bond within the molecule. So it's going to look something like this. This is indicative of a double bond between 2 carbons. I'm going to draw the hydrogens here, here, and here. And finally, propyne. This is indicative of a triple bond within the molecule. So it's going to look something like this. So we have a carbon here with all its bonds taken up. We have hydrogen, hydrogen, hydrogen. And this one can take 1 more hydrogen. So the answer is D. The with the least amount of hydrogens, which is 4. All right. So depending on, how you felt about the questions here, if you, did them all perfectly fine, straight away, no problems, then you're in pretty good standing to go ahead and take the test, I would say. I think it's definitely, the questions here don't cover every single topic, of course, but you're at least able to get 40 out of 60 on the local exam, which is good. So if you were having a little bit of a hard time, don't worry about it. These things, take practice and Sunday. So it's just we trying to understand where to apply stuff we've learned in chemistry to these kind of questions. All right, so let me clear these annotations. We're gonna move on to a little bit of history. Let's say someone type in the chat, are all these names familiar? No. We have a no. We have a yes. So history is important. I recall seeing questions about historical figures before. I'm getting some questions about Proust, Joseph Proust. I was not sure of his occupation. I know he was a really good chemist, though. And I know his law of definite proportions. But yeah, the law of definite proportions is usually just sort of skipped over, but it's sort of important because it helps us separate molecules from other molecules, pretty much. So I'll just go through it really quickly. There was some very smart Greek guy, Democritus, who, instead of thinking that everything was made from the 4 basic elements of water, fire, earth, and air, like the Avatar, he actually deduced that matter is composed of very, very, very tiny particles. I think the logic going of how he discovered that was he just kept breaking stuff until it was smaller and smaller until he couldn't see anymore, but he still knew it was there. Very smart guy. I think it took, multiple Greek people came to this conclusion, and that sort of started this Greek atomism sort of philosophy. And then years later, as everything is usually discovered in the 18th century, Antoine Lavoisier, who is known as the father of chemistry, came up and defined specifically what the law of I put conversation, it's conservation of mass. My bad, hold on. No one talks about mass, we conserve it. Conservation. I swear Word auto-corrected that. That wasn't me. Conservation of mass. So, which is defined as in a system closed to matter and energy transfer, the mass of the system remains constant. That's, pretty obvious until you actually think about what that means. What do we mean when we say a system? Why does the system have to be closed to matter and energy transfer? You can type it out, you can blurt it out. I recommend blurting, I don't mind blurting. There's some chats. I have some people saying, let me clarify what I'm asking. Why do we have to say the system is closed? And to address Jack's sad faces, it's important in both physics and chemistry. So if you know it in physics, I bet it also applies in chemistry. So someone indicated that yes, the system is closed, so energy is not lost or gained. And matter is not put into the system or lost from the system. And so the system sort of has this concept of, for example, if I react and light a piece of paper on fire, the chemical reaction of itself is the system. Usually, if you light something on fire, it loses the water molecules into the air. And people were thinking, oh, when they would weigh this, it shrunk, but actually the mass was conserved. It was just lost into the atmosphere, and they couldn't really hold on to it. There's experiments done where you have a flask and you light something on fire and put the top on, and you see that the mass stays the same before and after. So it's a system closed to matter and energy transfer. This is a little bit more advanced. Mike, could you please mute your mic? Hold on, I think I can do that. Hey, wow, that's a lot of power for a teacher. Yeah, so like Angela said, no reactants and products can escape. So why do we also have to talk about energy? You know, we're talking about mass here. Why does it matter? We're talking about energy. Anyone have any ideas? I have to do with a famous formula. Someone has nicely typed it out. Exactly. So it is E equals mc squared. So we know through Einstein's geniusness that energy can actually be converted into mass and vice versa. So if your system was not closed to energy transfer, then it's possible that it's possible that you could have a sudden gain of mass in the system on the quantum level. So this happens when you're doing reactions or things at the Hadron Collider, the particle hadron collider, where you would mash things into each other at such high energies that you would create mass out of it. So that system is not closed to energy. Does that make sense? I hope that answers some questions that I'm getting. Yes, the energy in the system has to remain constant. I'm getting asked to repeat what I just said. So whenever we've seen this sort of formula be used already, energy equals mass times the speed of light. This isn't the complete formula about the way, oh, by the way, there's like a little follow-up which has to do with momentum, but I'm not exactly sure what it is. I think it's like plus P. I think someone actually typed it. Is it P over R? Someone really good at theoretical physics. Anyway, yeah, so we're using a hadron collider and we mash things with such high energy we actually create mass out of it. Or we lose mass and it gets converted into energy. And so there is this conservation or loss, or there's this gain or loss of mass. Anyway, that was just a little bit of an aside. It's not incredibly important, but it's cool to know. So in 1779, Joseph Proust came up with the law of definite proportions. A chemical compound always contains its component elements in a fixed ratio. So what that's saying is, if I have salt, for example, salt is composed of sodium, chlorine, I'm not going to have something else that is sodium 2 chlorine and is the exact same thing as sodium and chlorine, right? This is a very different molecule. I'm not even sure this can exist based on electrochemistry or based on the electrons. So that's just to say, yeah, as Jack put it, salt is always sodium chloride, water is always water, etc. And that was a really important observation back then. It seems obvious now, but imagine what these people were working with. They didn't have our access to the tools we have today to confirm that's the case. And so finally, a lot of this culminated into John Dalton's atomic theory of matter, where he sort of took a lot of ideas from the past and laid out 5 different, I would say, hypotheses, because, well, I'll go through them first, but first one, he says matter consists of indivisible atoms, from Greek atomism. Makes sense, right? All atoms of an element are identical in mass and in other properties. Who could argue that? Different chemical elements have different kinds of atoms with different masses. Atoms are indestructible and retain their identities in chemical reactions. Atoms of elements combine with each other in small integer ratios to form compounds. So these, were revolutionary at the time and sort of formed a strong basis for everyone else to do chemistry on, because now they're like, okay, we know what we're working with these atoms and the molecules they form. By today, I think only 2 of these actually remain sort of true. We've sort of broken a lot of the atomic theory of matter with quantum mechanics. Can anyone guess which one of these don't hold true today, or you can list multiple of them? I think it's sort of fun to go over. So I have someone saying 2. So all atoms of an element are identical in mass and in other properties. Why do we say that's not true? Begins with an I. There we go, isotopes. So isotopes are atoms with more neutrons than protons, or different amounts of neutrons. Exactly. So we discovered these later, and that sort of makes 2 not correct. I also saw someone say 1, matter consists of indivisible atoms. So why is 1 maybe not true as well? What word in that? There we go. Someone said it. Atoms are divisible at the quantum level. Yeah. So we started breaking stuff pretty soon after, in like 1920. So I also saw someone say 3, different chemical elements have different kinds of atoms with different masses. I think that one, depending on how you interpret it, could remain true, actually. Different chemical, I may have put a very simple part of it, different masses. Only the mass part of 3 is wrong, right? That's also true. It's basically saying that, well, I think that is true, because it's almost impossible to have something have the same exact mass as something else. Even if we were to take away, for example, let's say we had carbon with 6 protons and 6 neutrons, and then we had oxygen with 8 protons let's say we had nitrogen with 7 protons and 5 neutrons. They would still technically have different masses. So I think 3 is the only one that has remained. the same. Yes. They have the same protons. No electrons. Yeah. Neon and sodium plus. Sodium plus would technically have 11 neutrons, so I don't think the mass would be the same. Wait, sorry. Sodium, that's the only thing they have. Sodium plus has one less electron, but it has more protons and neutrons, so the mass wouldn't be the same. I'm talking about the chat. Okay, anyway, I think 3 is the same. 4 atoms are indestructible. We already talked about quarks. And 5 atoms of elements combine with each other in small integer ratios. Turns out there are non-integer ratios that we've discovered, and these are in really complex metal molecules, metal ions, or metal compounds, where we might have 3/4 of a copper ion. It's the stoichiometric ratio sort of gets altered in that way, and it's pretty confusing. All right, so I see there's some discussion in the chat. I'll move on to the next part. So we're going to go over some basic structure of the atom facts, right? We are pretty familiar, I think, with this picture here. Oh, sorry. We're pretty familiar with this picture here, what we call the planetary model, where we're pretending like the center is the sun and the electrons are orbiting around the sun like planets. So this idea of a nucleus came from the experiment by Ernest Rutherford in 1911, where he was shooting what are known as alpha particles. So you have an emitter here, and we're shooting alpha particles. So alpha particles are helium nuclei, so it's +2. Right? There's no electrons there. Oh, sorry. Let me check my screen. Technical issues. Of course, this is Zoom. If there wasn't technical issues, it wouldn't be Zoom. All right. So as I was drawing out, we have this little emitter here shooting alpha particles, which are 2+, given 2 protons and 2 nuclei. They didn't know about they didn't know about neutrons until 1930, I think. They just knew that they were shooting positively charged particles. And they were shooting it at these films of gold. And so what would happen is, they have their little detector here. A lot of the particles, or a lot of the beam, would go through perfectly fine, but they would have random bounces in every other direction. And so the conclusion was, they'd say maybe 99% of the beam, they'd say 99% of the beam maybe went through, and the other 1% was deflected in all these directions. So the conclusion was, there's a lot of empty space in matter, right? There's a lot of, if this is the gold foil here, there's a lot of empty space that these helium atoms, which we know is matter and should interact with matter, is passing through. But there must be some tiny positively charged things inside all this empty space. And so when you consider what they were thinking of as the atom, it was just this like ball. They knew it was a particle, it was indivisible, and there was this tiny little center here that was positively charged, and then a bunch of empty space around it. And that would be what we'd call the atom. And so that's what gave way to this initial model. How do they discover neutrons? Did they do an experiment? Yes, they found out with, I think, I would call it archaic mass spectrometry, that the mass charge ratio, we'll get into it, but they basically found that the charge didn't match the mass, and that the charge was about half the mass at each time, meaning that there was something else that wasn't charged but was providing mass to the molecule. I'm answering a question in the chat. Sorry. All right. So we know this model is a really nice, pretty one, but it's not exactly the whole truth. Instead, we have what we consider now more accurate, an electron cloud model, where electrons aren't particles, but they are wave particle constituents, where their location is defined by a probability, and we have this probability cloud surrounding nucleus here. You know, and the nucleus is a positively charged center. And I have just some facts here. Protons weigh very little, neutrons weigh very little, electrons are very, very light. There's a question in the chat. Is this recorded? Yes, it is recorded. I'm not exactly sure how you would access the recording. You'd have to ask someone at Momentum Learning, but it will be available, and it's in the cloud, so it would be accessible to whoever needs it. So anyway, I bring up these masses because I think it's really interesting to see the disparity. You see how light electrons are, and you see how the maximum, the most of the amount of mass we're talking about when it comes to atoms come from the center. There's a little bit of extra numbers that come after the sevens in both of these, and I tried adding the electron mass to the proton mass, and it got really, really close to the exact mass of the neutron, and I thought that was also really interesting. But, you know, these are incredibly small numbers we're measuring, so I'm not even sure about the accuracy of what I'm doing. Anyway, any questions so far? Sorry if I'm going a little too fast. All right, no questions. I'm going to clear the board, and we'll move on. So in addition to what makes an atom, we have to consider electromagnetic radiation. So the concept of light is pretty complicated. We don't really cover it in detail in chemistry until you get to quantum chemistry. There's four laws that dictate what light is. I think it's Maxwell's laws. But just know, according to answer the question in the chat, the blue right here is the electric field, which is perpendicular to the magnetic field here. And so when these two fields interact, they propagate according to the right-hand rule, and we have the traveling velocity of light in this direction. So yeah, V, I believe, is just the term for, I think they're saying velocity. It's definitely velocity, but that is the direction that light is traveling. So just a little bit of facts. Who can tell me what the speed of light is off the top of their head? So I already see it. Yep, 3 times 10 to the 8 meters per second. What is this length called here? As wavelength, correct. Wavelength is important. So, and I suppose we know what frequency is. I don't know if I have a good way of drawing it out, but you know, the amount of times that we see the periodicity of the wave going forward. So we have this is equal to frequency, which is in units, 1 over seconds. This is in meters. So unit of length, this is a unit of inverse time. And so we know for light, this always holds true. The wavelength times the frequency, in a vacuum at least, is always equal to the speed of light. This is also true if you're trying to calculate the speed of other waves. You get the wavelength, you multiply it by the frequency. But in regard to light, as we know light always travels at this speed, we always know this formula holds true. And with regard to frequency, can anyone tell me what the energy of light is equal to? The energy of a photon. I see an answer, HMU. H times U. Ah, yes. So that is H times frequency, where H is Planck's constant. I don't recall how Planck's constant was discovered exactly, but I remember it was a really cool story, and that guy was really smart. This is approximately equal to 6.623 times 10 to the negative 34. So this is frequency. 626, yes, you're correct, not 623, sorry. Getting my significant figures wrong. So those are some just basic features of light. And then we move on to the spectrum of light here. So I'm sure y'all have seen some variation of this before. I think it's really important to remember off the top of your head exactly the order. Just, you know, you got to know it by heart. So we know it goes radio, and then micro, then infrared, or IR, and then visible, and then ultraviolet, and then X-rays, and then gamma rays. You should just know this off the top of your heart. It's really handy. And you should know the visible spectrum is from about 700 nanometers to 400 nanometers, where the nanometers refers to the wavelength of light. And we also know that this is in increasing frequency, as you see here, but also increasing energy. So we have radio waves blasting us all the time, but it doesn't hurt us because the energy is so low that it can't damage our DNA. However, if some mad genius scientist wanted to invent X radio waves, where he sent X-rays out to try and communicate or send music, we'd be giving everyone cancer. Dark lines on the spectrum means energy is absorbed. Oh, I just think that means we can't see it. I think that's what they're trying to say. That's my interpretation of this graph. I think you're referring to emission spectra, which we'll get to very soon. But this is just saying that we can't see past here or past here. But also Roy G. Biv, really important to know your rainbows. So from the 700 part to the 400 part. All right. Any questions so far? All right. So let's go onward to, I think that is my next slide, the Bohr model. So you can see the Bohr model was presented by both Niels Bohr and Ernest Rutherford, and they took the planetary model to heart, where they have our nucleus here and our orbiting electrons there. So with nucleus, the plus ZE refers to the positive charged center, where E is the number of electrons in the atom. So this is a very important stepping stone we had, because it defined what we now call electron energy levels. And so depending on how excited an atom is, we can see what the energy levels of the electrons in the atom are. And the reason that this is important is that automatically indicates that there is a non-excited level of the atom, also known as a ground state. So a ground state means that the energy of the atom is at a minimum, where all the electrons are at the lowest energy level possible. So this is sort of just a basic overview of the Bohr model. I wanted to ask, what are some assumptions being made already that we can see? Only one electron in the atom. Electrons travel in perfect orbits. These are great. So yeah, the model tried to account for multiple electrons, but they found out that the model only works with the hydrogen atom. So only with a 1 proton and 1 electron system, the model is able to accurately predict how a hydrogen atom works. Electrons traveling in perfect orbits, yeah, it's not Earth, you know, we have this electron cloud, and usually electrons, when they travel, they're going all over the place. Any other assumptions? So I have a pretty important one. The idea of the ground state in the Bohr model indicates that the electron is right here, and it cannot go any closer to the nucleus. But that's not exactly true. If we think about our electron cloud model, where we had our electrons flowing around in here, it is possible, but very, very, very improbable that you would find an electron right here, right? The electron probability density dictates that it's somewhere all over in, this region 99.999% of the time. But having it go into the nucleus is technically not forbidden. So that's an interesting fact that comes out of quantum mechanics. And if this class goes forward in a more advanced direction, I would cover the Schrodinger equation, what specifically are orbitals for electrons, how they look like. It's really cool stuff. But for now, it's good to understand the limitations of the model. So we'll move a little bit forward here. Any questions, by the way? All right. Angela speaks for everyone. She says no, so there's no questions. I'm just joking, but you can. All right, let's move forward. So a little bit of a jump. This is exactly what people were referring to before, the atomic spectrum of hydrogen. So this is important because the Bohr model was sort of used as an explanation as to why we saw these little lines here. And so as someone said, these black lines are indicative of the electrons. So let me explain the experiment first. We have a sample of an element. For this instance, the element is hydrogen. And we are shining a light and exciting the electrons inside the hydrogen. And so we have the emitted spectra coming out, or whatever comes out coming out into a prism, and we're able to separate the emission lines into a little detector here, and this is what we see. So we see that there's these lines, and these lines are, at first really, really close together, but as you get farther and farther with increasing wavelength, the lines are they have larger gaps in between. So trying to explain this with classical physics was impossible, because classical physics and classical theory did not take into account the possibility that energy levels are quantized. And so what do I mean by quantized? I'm saying that whenever we have a little proton or a little atom here, and we have our orbitals here, according to the Bohr's model. We're working with only hydrogen, so I'll erase a lot of these circles. We have our little proton here, and we have our little electron here. Whenever light shines on it, the electron doesn't, move halfway in between and then come back, or halfway, 3/4 of the way to the next orbital, or 1/4, it moves the complete energy level. So this is n equals 1 being the ground state, and this is n equals 2. There is no halvesies here, right? The proton is able, or the electron is able to move entirely to the next orbital. And so these energy levels are discrete, meaning they're whole integers, and it requires a specific amount of energy to complete the jump. And when I say there's quanta involved, so quanta means packets, and the packets refer to the photons that are hitting the electrons and exciting the electrons in a specific amount. So, it doesn't take 1 1/2 of a proton. It takes, or 1 1/2 of a photon to excite an electron. It takes 3 photons, a photon, and if it has the correct amount of energy, it'll make the jump. And so transitions between energy levels are quantized. Does that make sense? I know this is a bit of new terminology. Dark means, okay. So this is a really important realization scientists had back then, and sort of led to the need for the development of a quantum theory to understand chemistry and the substances around us. So I'm going to go to the next page. Let me clear the annotations. So continuing on the idea of the atomic spectrum, we were able to empirically develop a formula which was later confirmed using the Bohr model that describes or accurately calculates the amount of energy being released from a transition in the from one orbital to the other. And so the equation right here, the Rydberg equation, also known as the Bohr equation, calculates the emission frequency using the Rydberg constant, which they found and confirmed empirically through experiment. And these numbers here refer to the energy levels, where N1 is the starting energy level, the initial energy level before the electron is hit by a photon, and this is the final energy level. And so there's multiple constants depending on what you want to calculate, right? I have emission frequency here. If I wanted to calculate the emission energy of the photon, then we would use a different constant. I think I got a question just now about the Rydberg constant. So the Rydberg constant is used for whatever the placeholder is here. I can show you how we get from one equation to the other. So if I wanted to find the energy of the proton or of the photon instead of the frequency, I would multiply both sides of this equation by Planck's constant. So we have h frequency equal to h times RVh, 1 over n to the 1 squared minus 1 over n to the 2 squared. And we realize that this is equal to energy, and this is equal to RH. And RH is the Rydberg constant specifically for energy, while this is the Rydberg constant, this RVH, is specifically for frequency. So that's how we convert or use the constants differently, depending on what we want to find. And so this little sequence here, I think someone did a good job noticing and defining what levels of light these correspond to. Basically, the Lyman sequence just finds the difference between different energy orbitals and the ground state, the energy orbitals, and the second, energy level number 2. And there's other sequences that aren't pictured here. And they found that the hydrogen atom emission spectrum matches the findings for the Rydberg formula. So does anyone have any questions about all this? All right. So I think in the test, you're given this formula. So you don't have to memorize it, but it's not too hard to at least memorize that you have to take the inverse of the energy level and subtract them, and then multiply it by some constant. So I have a question. Is this related to Planck's constant or equations related to that? Just wondering. So Planck's constant is used in almost everything. Basically, whenever you want to find the energy of a photon, you use Planck's constant. So we'll move on. So this is a quick quick turnaround. Who has heard of mass spectrometry? I think I mentioned it really quickly before. Oh, sorry. Stars and stuff. Yeah, I think I actually don't know how you'd use it for stars. That'd be intense. But I'm sure scientists have found a way. NASA's really smart. But just a quick little overview. Yes, so the mass spectrometry is a technique used to determine the mass to charge ratio of ions. And this is the now standard way of determining the chemical composition of any molecules. There's many different types of mass spectrometers. There's mass spectrometers for proteins. There's that weigh, 100,000 to 500,000 grams per mole if we had a mole of the protein, or atomic mass units. There's tandem mass spectrometry, where they're able to split large molecules into smaller and smaller pieces. It's really impressive technology. So the basic concept is we have a little sample here that we ionize by firing a really strong electron beam at. So when we fire this electron beam, today's class is until 5:30. Am I going over time? Oh, 3 minutes. I can finish up pretty quickly. I'll just go over some of the basics of mass spectrometry really quickly. And then I hope if you want to stick around and ask questions, you definitely can. So the sample is put in the mass spectrometer. We fire a really strong electron beam, and this electron beam rips off electrons from the molecule. And so now it's ionized, meaning it has a charge, and so if we apply a magnet to it, it will influence the trajectory of the molecule. So we're firing it, and depending on the mass of the molecule will affect how severe the trajectory is changed. So the heavier something is, the less affected it will be by the magnet. So as you see here, if it weighs lighter, the magnet's able to pull it closer to itself. And this is just, a detector, collects the information, and it tells you the mass of what the mass of the atom is, and the relative intensity, meaning how much of it there is. So if we go on to the next part, this is the atomic mass spectrum of oxygen. And so does anyone want to explain why we have maybe two peaks here? Note the axes and what they mean. Relative intensity. O and O2. Someone has correctly identified. Oxygen in its normal state is actually O2, and O2 is 16 plus 16. But whenever we put this in a mass spectrometer and we fire a super concentrated laser of electrons, we're able to actually break the bonds between the oxygen atoms. And so we get some oxygen atoms here, plain oxygen atoms. So I think the photoelectron spectrometry, I think I know what you're talking about, but that's something different. Sorry. So let's go on a little bit more. So this is the mass spectrum for chlorine. And can anyone explain why we see the peaks here that we see? And then this will be the last slide. this and the next one. And then we can go ahead and end class. Any takers? Chlorine, by the way, on the periodic table has 17. No, it has 31 protons, I believe. Mass 35. Thank you. 35 protons. So, yes, as some people are saying, chlorine has, in its normal state, is also paired with itself. And again, when we break it apart, we see that this refers to chlorine on its own. And something special about chlorine is its isotope. So chlorine is usually, I believe, 70, 35, but it has a common isotope, or not. Let me clear that. Usually chlorine has a isotope with 35 protons, or sorry, has a common isotope with 17. If someone can correct me on this. In any case, the isotope of chlorine influences the total mass that we see here. So whatever normal amount of protons and neutrons that chlorine has, there is an isotope where it has 2 extra neutrons. And so that's what we see here, this peak here at 35, and we see a separate peak here at 37. And what about this peak here? What is this reference to? So we have I'll just go ahead and explain. So in our chlorine, whenever we send it through the spectrometer, it could either have the typical number of neutrons, or one of the atoms can have the +2 amount of neutrons, or both of them can have +2 neutrons with them. So if that's the case, we see that the peak here is in reference to this species of chlorine molecule that we're sending through. And this sort of becomes a mathematical question where you determine the relative ratio of the molecules we see. So we see here that the chlorine typically has about 25%. 24, we usually simplify it to, if you were to choose any random 4 chlorine atoms in the universe, about 1 out of 4 of them would have this special isotope here, chlorine 37. So we see that here. This has about a ratio of 1 to 3, let's say, where this is about 3 times as high. And then here, if we were to do the math, we would see that this is a ratio of 9 to 6 to 1. And that's just from going through and taking this ratio and considering the possible combinations you have. This would be chlorine 35, 35, 35, 37, and so forward. All right. That's just a little bit of the basics to mass spectrometry. There's, it can get a lot more complicated. So if I go here, this is octane, which is C8, H18, and we see all this fragmentation here because we ripped the molecule into pieces. And so trying to identify something becomes more complicated once we start getting into more complicated molecules. Anyway, I know we are 6 minutes over time. My apologies. Please feel free to ask any questions, or if you need to go, you can go. It was a pleasure to, teach some of this stuff. Sorry I had to rush some at the end, but I have a bit of practice questions here that I was going to ask at the end related to what we just covered. So, but time's up. Any questions, please, feel free. All right, so I have a question here that the x-axis is the mass to charge ratio. So this is important because, yeah, we can only measure charged ions. And so usually we get a charge of +1. And we go back to the other. So I'm currently using I have to actually pull it up. Let me go ahead. I believe it's called The Principles of Modern Chemistry. There's multiple editions online. All of them work. Chemistry hasn't changed entirely too much back then. Principles of Modern Chemistry by Daniel Oxtoby. Type that in the chat. So if I was to recommend a book that covers the general stuff, is The Principles of Modern Chemistry by Daniel Oxtoby. I think his first name is Daniel. Any edition, whatever you can find. Oh, sorry, that is too. There you go. If you really want to be a go-getter, which I totally recommend, the organic chemistry book I would recommend. It's a relatively small one, but everyone in my college used it. I think it's Organic Chemistry by someone named Klein. Whoa. Sorry, I think I've been signed out. Can everyone still hear me? Is that David Klein? Yeah, it should be not a big book. Yes, Organic Chemistry as a Second Language. So I was also going to answer the other question. Where would this compare to high school courses? Are you asking what this class specifically would be? I would say this would be a little bit more advanced if I was to go through more advanced in AP chemistry. but almost along the same lines. I think I would just put a little bit more of the advanced stuff in the middle or interject. But you should definitely be able to. I would recommend this class if you've taken regular chemistry already in high school, or you've taken the high school level regular chemistry. So the organic chemistry textbook by David Klein. No, you're okay, Irini. Was this a sample of what would be in the first class? Yes. I think I might try to make it a little bit more elevated depending on the people who would sign up. This was a general audience, so I try to temper it and put it in the middle. I honestly think if you're able to take AP chemistry, that will do a fantastic job covering what I would cover. So I think if you want to learn more advanced stuff than what you learn in high school, this would be the class. So bye, anybody who's leaving. Thank you for joining me. Hope that was informative. Please feel free to stick around. Will I share the slides? Sure. I'm not against it, but it depends on Momentum Learning themselves. So will I share the slides? Yes. Will Momentum share the slides? I'll have to ask them. I recommend if you want to get to nationals, leading up to the competition, I would take a test every day. There's the whole collection of tests that have been given in the past are available on the American Chemical Society website. I've downloaded all of them. I've pulled some from today already. What do I recommend memorizing? Oh, I personally don't like memorizing a lot. I try and see if I can navigate a lot of questions based on just the principles. But unfortunately, there are some things that you just have to know. Yes, the flame tests, you'd have to know the colors of what you put, or the sort of lights that would come up if you put sodium in a fire. You have to know what makes soluble or insoluble molecules. You should know the general trends for electronegativity. Am I going to post practice problems? The ones that I had at the end of the slides? Yeah. Oh, I'd really like to. I don't know where I would post it though. So I think maybe if y'all can really quickly, just to make sure you don't miss out, can you screen cap these pictures? So let me know when to move on to the next one. To answer your question, Harini, is sodium, I believe, is yellow when you put it in the fire. Copper is greenish blue. Potassium is like violet. I'm a little bit colorblind, so it's always been hard for me to like distinguish. All right, can I move on to the next slide for those? All right, if you know lead iodine specifically has that color, that's fantastic. It seems like a lot of y'all know. How many of y'all have taken AP chemistry? Lead iodide. Oh, I don't exactly remember the color tests, if I'm honest. Taking AP chemistry next year. Yeah, I think taking AP Chem prepares you for the local exam almost entirely. You won't get organic chemistry. You'd have to study that on your own or through here. But AP chemistry itself usually prepares you for the local exam. Yeah, 80% is definitely from AP chemistry. Someone has entered. Wait. Oh, let me move on to the next question, I guess. AP chemistry in 8th grade. I don't know who's that smart. Oh, in like 3 years. Yeah, I took AP chemistry in 10th grade. So what school did I go to? I went to Harmony School of Advancement, if y'all have ever heard of that. I went to, for college, Stanford University. Go to the next slide. Everyone else agree? All right, this is the last one. This is just sort of, can you clear that little blue line? Can you understand what a mass spectrum looks like? If you already know, if you already understood what we were going over, that'd be perfectly fine.
What was it?
Still going.
Still?
Yeah. Mass spectrometry, yes, mass spectrometry would definitely be on the test. I'm answering questions.
Still, to 5:30, they can. How many minutes?
Yeah, everything we talked about today could be on the test. Especially the national exam, the free response varies over everything. I think if you go and you take a look at the local, yeah, this is the last question, by the way. If you go and yeah, that's it, just 4 questions. Sorry to disappoint you. Let me stop sharing. If you go and you take a look just at the local exams side by side, you can see that they all have a very similar structure in the type of concept they cover. Usually it goes over something generic, something like a trivia question, and then it goes on to solutions, and then it goes on to stoichiometry, acid bases, and it's pretty incredible how organized it gets. So I started to like anticipate what kind of question would come. Yes, from the local exam and the national multiple choice exam. It's pretty categorized, yeah. So if you're like, oh, I want to do the organic chemistry part first, it's always at the back. Not always, but like 90% of the time, it's at the back. Anyway, I have to go. Thank you so much for sticking around. Consider the class. Give feedback if you can. Tell them you want something either harder or easier. Thanks all y'all for coming by. Hope you have a good Sunday. I'll sign off now.